So far this term, we've looked at angles as though they always start from this position here. We say that that angle is 0 degrees or 0 radians. In the navigation world, though, we look at things a little differently. Here's my coordinate axes. I'm either going to say that, or think, of this sort of due north is as 0 degrees, or due south. And if I want to indicate then, for example, this angle right here, I would indicate that by saying that the angle I was interested in, this one right here, was so many degrees to the west of north. Let's say that this angle in here is 40 degrees. In terms of navigation, I would give this bearing as north 40 degrees west. In a different example, I would give this angle, let's just call this one 40 degrees too. Remember, this is north, and I'm saying that that's 0 degrees. And actually, this is south. That's also 0 degrees. I know that's a little tricky, but bear with me. This angle right here is north 40 degrees east, because I'm starting facing north and going 40 degrees to the east, to the right. All right, there are two more instances, and those are ones where I start facing south. So if I'm in quadrant 3 or quadrant 4, I might call this angle south 40 degrees west. And this last one is south 40 degrees east. So this is just a different kind of notation, a different form of recording the angle that you're looking at. So far this term, we've just looked at a 360 degree or 2 pi rotation. We've recognized that we can go around multiple times. So we can have 360 degrees or 720 degrees, or we could have negative 360 degrees. In the navigational world, though, we're only going to have angles that are between 0 and 90 degrees. They'll either be between the vertical here, which is the north pointer, and the left pointing pointer, pointing west here. You have to know your north, south, east, and west. If you're looking at a compass rose, for example, if you've ever seen those, they usually look something like this. North is always up. Now that wasn't always the case. So if you're one of those map nerds, don't get mad at me here. I'm just trying to convey what's common and conventional now. Okay, north is up on a map, south is down, west is to the left, and east is to the right. So the west coast of the United States is where Seattle and Los Angeles are, and the east coast is where New York is, for example. In between north and east, we have northeast. In between north and west, we have northwest. Then there's southwest and southeast. And notice how the north or south always comes first when we're describing these in between directions, right? So that's kind of what we're doing here. We're saying northwest, northeast, southwest, and southeast. One of the nice things about this new notation is that your angle is always only ever going to be between 0 and 90 degrees. One of the less nice things, as far as I'm concerned, is that the notation feels a bit messy to me. But that's just how it is. If you go into any field that requires you to learn navigation, if you learn how to fly a plane, then you're going to need to know this type of notation. So this is really just an application. There are a couple of things I'd like to talk about just very, very briefly before we move on to an example. One is that the thing that I've been talking about here is called bearing. We say, for example, that the bearing of the aircraft was south 40 degrees west in this example. The other thing is that there is another convention sometimes used, and that is that the measure is always taken from north. So in that instance, in that convention, I could give the bearing for this angle as, that would be 90 plus 40 in that case, so that's 130. I would say 130 degrees west. I also might say north 130 degrees west, but in that case, I don't really need the north because in this world, in this convention, it's always north first. We'll stick with this convention. This is just an application, and so I'm really just interested in giving you some exposure to the idea. So we don't need to get too much into the weeds about which notation is right or which one's better. We'll just use the one in your textbook. Let's take a look at an example. All right, this one's pretty wordy, but let's read through it and see what we've got. A boat leaves the harbor entrance and travels in the direction south 9 degrees east. This is what we call a bearing. When you see the word bearing, what it means is the direction that the boat, in this case, is pointing. It's pointing south 9 degrees east as it travels. After 22 miles, the captain makes a course correction and changes direction to north 50 degrees west. After traveling 21 miles at this bearing, how far is the boat from the harbor entrance? And what is the bearing of the boat from the harbor entrance? So we have two questions to answer here, but let's start with a diagram. Let's say the harbor is here. From that perspective, the first direction of travel is south 9 degrees east. This is south. 9 degrees east of south is not very far, but it's in the east direction. So we're traveling in that direction or at that bearing for 22 miles. At that point, though, we change course. And now we're going to go north 50 degrees. Which way? North 50 degrees west. So north and west is here. If I go north, which would be kind of like my y-axis, and I go 50 degrees west of that, I'm going to be over here somewhere. So I'm going to try to imagine that there's a perfectly vertical line here. You can almost think of this little crosshairs down here that I drew as like a mini set of axes. And what I want is a line that goes off into quadrant 2 at about 50 degrees. So that would be about there. And we're going to do that for 21 miles. And this line actually should be a little bit shorter than the other one because one line is supposed to represent 22 miles and the other one 21 miles. Now, it doesn't need to be exact, but you get the idea. I hope you get the idea. All right, and now the question is, so this is where at the end of that 22 miles and then 21 miles, this is where my boat is now, right? So the first question I want to answer is how far is the boat from the harbor entrance? So that's going to be represented by, wrong pen, sorry, this distance here. I'm looking for the length of that side of this triangle. Let's go ahead and do that first. I'm going to start by moving my diagram, which, as you probably know by now, means taking a minute to do that live and in person, since it won't let me do it off screen. There we go. And then I'm going to, there it goes. I can't move this one last piece. There we go. I'm going to blow this up. I'm going to take this little crosshairs that I drew down here and blow it up a little bit so that we can look at, first of all, I'm going to do this kind of backwards. We can look at this first, this line segment that goes out into quadrant 2 at 50 degrees west of north. That's about there. And then take a look at this line coming into quadrant 2 from up here. From here we went, what was it, 9 degrees east of south. So we went south 9 degrees east. And so I'm going to do that, but I'm going to look at it from the perspective of it coming into quadrant 2. That might look something like this. And remember that that was coming from another location, another position up here. And if I take that horizontal and vertical, the vertical specifically, and kind of draw it in, you'll notice that this was our 9 degrees. We came in from here, south 9 degrees east. So this is a 9-degree angle right here. Well, now take a look at this. I have parallel lines here. Well, they're not really very parallel, are they? This is why I'm a math teacher and not an art teacher. One reason among many, anyway. But these are parallel lines, parallel vertical lines. So if this is 9 degrees, this is also 9 degrees. Let's mark that. Let's do it in a different color. This is 9 degrees. But this is my vertical, right? This is like my y-axis, and this is my horizontal. So, and this angle, let me use a different color again. This angle from the vertical, from this position here, from this perspective here, this angle was 50 degrees. Is it 50? Yes. 50 degrees west of north. So you can see now that this 50-degree angle minus this 9-degree angle is what's left in here. And so this is a 41-degree angle. So it's a bit involved. There's some thinking you have to do to get to the place where you know how big this angle is that you want to work with for this problem. This angle is 41 degrees, 50 minus 9. And so that is this angle right here, 41 degrees. And now what we have is a side angle side. So with side angle side, I can solve this for any of the other 3 pieces of this triangle, either this angle, or this side. I may have to go through solving for an angle to be able to solve for the side, but I can do it at this point. And that's what we're going to do next. I'm going to find the length of this side, but because I have a side angle side, the only tool I really have at my disposal is the law of cosines. The law of cosines says that a squared equals b squared plus c squared minus 2 times b times c times the cosine of a. Now, I'm going to let this be little a. Let's use pink for that. Okay, so there's a. That's little a. So that means that a is my unknown. But equally, angle A, which is the angle across from side A, is 41 degrees. So when I get over here, this is going to be cosine of 41 degrees. Now B and C can be either of these other two sides. So B and C are 21 and 22 respectively. So I'll call this 21 and 22 minus 2 times 21. I've run out of room. Times 22. And the rest is calculator work. Remember to make sure that your calculator is in degree mode. But when you do that, you should get a squared is approximately 227.6483. And you take the square root of both sides and you get that a is approximately 15.0880. So my answer, at least to the first question here, the length of side A, right here, represents the distance from where the boat is back to the harbor. That is the answer to this question. How far is the boat from the harbor entrance? The second question was, what is the bearing of the boat from the harbor entrance? Well, that's a little bit trickier. Notice that where the harbor entrance is back up here. And what we have to figure out now is, let's say I've done it in one diagram, I'll do it in this other diagram. That's where the harbor entrance is. What we have to figure out now is not the distance of this line segment, the length of this line segment, but it's how far. You can tell that it's south and west, but what is the number of degrees south and west this line segment is from the vertical? So that's the next job we have to do. I think that in order to explain this, I want to start with a brand new diagram down here. So I'm going to leave that one there, but I'm going to draw a new one, a new blow up. This time my blow up is this is the harbor, right? So this is our starting point. We came down 9 degrees east of south. Then we went back out from here 50 degrees I can't draw a straight line, 50 degrees west of north. This right here, I'll do it as a highlighter. This right here was a 9-degree angle. Right, and we also found another way to represent, let me get a different pen again. This was also a 9-degree angle. And that was important because, I'll go back to my original diagram instead of this one here, come back over here. This was a 9-degree angle, and that was important because this whole thing from the vertical here, this whole thing was 50, and if that was 9, that tells me that what was left was 41. So that's how I got this angle here. But now I want to use the original 9 degrees again. I want to find the angle formed by these two line segments right here. And I have the law of cosines and the law of sines now, so I'm looking for this angle right here, and I know that what that angle is, the total angle is going to be, let me use a different color highlighter, it's going to be this white angle plus this yellow 9-degree angle is the total angle formed by those two line segments. So I can find that total line, that total angle, but I'm asked for the bearing of the boat from the harbor entrance. So what I really want ultimately is just the white angle. But that's okay, because once I've found this whole angle, I just need to subtract 9 from it. All right, so let's go find this angle. It's this angle right here. I could use the law of cosines. I've got my angle A here because it's across from side A, but I haven't labeled either of the others. So let's go ahead and do that real quick. Let's just call this angle B, which makes this side B, and angle C is here, which makes this side C. And then, because I'm looking for this angle right here, I'm probably going to want to use C squared, which has to be this side over here, 21, C squared equals A squared plus B squared minus 2 times A times B times the cosine of C. And I don't know what C is. I do know what A, B, and C are. So I'm going to have this formula, a different version of it, this formula. But instead of A being the unknown and everything in here being a number that I can just crank out on my calculator, the first thing will be a number. All of these will be numbers. This will be a number, and this will be an unknown. And I'll have to use the version of the cosine, the law of cosines, that solves for the cosine of A first and then takes the inverse. We've done that. We looked at a couple of examples of that, and it's perfectly legitimate to do it that way. But there's another way. Right now in this diagram, I have a side. Let me color code these sides here. I'll start by changing A from pink to green because now angle A and side A are across from each other, are the same color. I think I'll change angle A's color as well. And then I've also temporarily removed the H that I had representing the harbor entrance here. I'll make angle C yellow, and so I'll make side C also be yellow. And B, let's see, what should we do for B? What color should we make B? I've got blue and green, sorry, yellow and green. I guess I could go with pink. Side B is 22 miles. And let's change angle B to pink as well. Okay, now we don't know angle B and we don't know angle C. We do know angle A. And now we know all three sides. In fact, let me go ahead and stick A in there. Just for record keeping purposes, I'm going to call A 15.1. And so all that's missing now are these two angles here. And this is the angle I'm looking for. Notice though that it's opposite a known side, the unknown thing, the thing I want is opposite a known side. So I could say, for example, the sine of C over side C, which is 21, is equal to, now all I need is a pair of opposites where I know both of them. So I have two opposites left, A and A and B and B. And A is a rounded number, so it's less than ideal to have to use A and A, but I don't know angle B at all, so that's really not an option for me. So I'm going to use A and A. So I have sine of A, which is 41, and that's opposite side A, which is 15.1, which is a highly rounded number. So I won't actually use 15.1 in my computations, but for record keeping purposes, that's how I'm going to write it down. And now all I have to do is solve this problem. I have 15.1 times the sine of C equals 21 times the sine of 41 degrees. Divide both sides by 15.1, and my computation now looks something like this. Let's see, those cancel. I end up with the sine of C is equal to 21 times the sine of 41 degrees over 15.1, which on the calculator looks a bit more like this. 21 times the sine of 41, the calculator is in degree mode, divided by 15.1 was my A value. How did I get that? I got it by taking the square root of this rounded value. And I got that by doing this computation here. So I haven't thought forward far enough to be able to just look back up the screen and find this value here. But if I start scrolling anyway, scrolling up on the calculator that I'm using anyway, one of my very most recent computations is 15.0880200. It's the answer that I got here without rounding it first. So if I scroll up and find that value, and the calculator has it highlighted right now, when I hit enter, I get that value in this position. So my calculator is actually going to use the unrounded value to do the computation. Now I'll hit enter, and I get that the sine of C is approximately equal to 0.9131. It's not that rounded, but that's good enough for me for right now, for record keeping purposes. And then I'm going to take the sine inverse of both sides, which gives me C is approximately equal to second sine second answer, enter, 65.9408 degrees. So I have found angle C, which is this angle right here, and it represents or is represented by this angle right here. But remember, I'm looking for the bearing of the boat from the harbor entrance. So I don't want the whole angle. I just want the part of the angle that's to the left of the vertical line here. So I got to take this whole angle and subtract 9 from it. Minus 9 gives me 56. Answer. 56.9408 degrees. And that is the answer to this second question. Now that has taken me almost 20 minutes to walk through with you and explain. And I'm not going to apologize for that. I think this is a really good example of a problem that gets you to use the things that you're learning in a class for an actual application. All right, you may not be captaining a boat anytime soon, but it's a real situation in which you have to actually think through logically, what do I actually know here? How can I use previous knowledge to determine the pieces of information that I need to use to answer this question? And what is the real answer to my question here? What are all the pieces and how do they fit together? And what do I need to add and subtract and why? I think this is a really nice problem. Our next application is a little bit more straightforward. We'll talk about that in the next video.